If you are staring at your IDE right now, wrestling with an AI model that just confidently wrote 20 lines of completely hallucinated garbage, well, you are in exactly the right place.
Yeah, you really are.
Tonight, we are talking directly to you, the software engineers, the builders out there who are trying to figure out how to take large language models and make them actually reliable.
Because that really is the main hurdle right now, isn't it?
Oh, absolutely. And we have a really fascinating stack of notes tonight, focusing on a concept that sounds, almost human: self-reflection.
Right.
We are going to unpack the exact mechanisms, the hard limitations, and the specific frameworks that allow an LLM to check its own work.
Okay, let's unpack this.
Let's do it. Reliability is the frontier we are all pushing toward. We've moved past the initial awe of just watching a machine generate text,
Yeah,
right?
the parlor trick phase is over.
Exactly. Now we are squarely in the phase of figuring out how to trust the architecture behind that generation. And self-reflection in AI, it is some mystical, sentient process. It's not actually thinking about what it did.
No, not at all. It is a highly specific engineered loop. Understanding how that loop functions is the key to building robust applications, especially when dealing with, complex logic or code.
Right. If we think about it in human terms, an LLM is essentially like an ultra-fast, incredibly well-read junior developer.
That's a great way to look at it.
So self-reflection is basically asking that junior developer to proofread their own pull request before they actually submit it. You want them to catch their own typos, spot the logical errors, fix the syntax.
Right. But we know how that goes with humans.
Exactly. And I imagine it is even more complicated with a machine that just predicts the next word. How does a model actually do that?
Well, with a human, asking them to look closer relies on their internal capacity for continuous critical thinking. With an LLM, which operates as a next token predictor, you have to build a structured generate, evaluate, improve loop.
So it's not going to happen on its own.
It will not happen organically. The model generates a first draft. Then you use a separate specific prompt to evaluate that draft against certain criteria.
Yep.
And finally, you feed that evaluation back into the model to generate an improved version.
So you are basically prompting it to argue with itself through a series of distinct API calls.
That is the mechanical reality, yeah. And this is where the frameworks from our sources, like Self-Refine and Reflection, provide the necessary scaffolding.
Because they structure that argument.
Right. They turn a static prompt into a dynamic, multi-turn process. Reflection is particularly noteworthy because it maintains an episodic memory.
Episodic memory. Let's look closer at that. What does that actually look like in the payload? Are we just like stuffing the context window with a massive history of every single mistake it just made?
No, it is a curated history.
Right.
So in the first iteration, the model attempts a task, say, writing a Python function. It fails. The system captures the error. Reflection then prompts the model to write a short, specific diagnosis. That's the reflection.
Yeah.
In iteration 2, the prompt includes the original task, the text of the first failed attempt, the error log, and that specific diagnostic reflection.
So the context window is holding the trajectory of the problem-solving attempt, not just the isolated current state.
Exactly.
Here's where it gets really interesting to me. This generate, evaluate, improve loop, complete with a log of past failures, it sounds exactly like a CI/CD pipeline or test-driven development.
Oh, for sure.
Like you write the code, the automated tests run, they fail, the pipeline spits out an error log, and you use that log to rewrite the code. Except here, the model is writing the code A and D, running the unit tests entirely in its head. It is playing both roles.
The CI/CD analogy is perfect because it highlights the necessity of the pipeline. You wouldn't trust a developer to push directly to production without tests.
Definitely not.
The reflection framework acts as that automated test suite, attempting to move the LLM from a one-shot response generator into a continuous improvement engine. It forces a standard of quality before the final string is returned to the user.
But wait, if the model's playing both roles, what happens to the pipeline if the test suite itself is fundamentally flawed?
Right.
What if the unit tests were written by the exact same developer who wrote the buggy code, and they share the exact same blind spots? If the tests are wrong, the pipeline passes green and you deploy a broken feature.
That brings us directly to the self-verification
The
paradox.
self-verification paradox.
Yeah, this is a massive structural limitation in current self-reflection models. The exact same knowledge gaps that cause the model to make errors in its initial generation are the very gaps that prevent it from detecting those errors during the evaluation phase.
So what does this all mean? If a model is confidently wrong because it literally doesn't have the data or the reasoning pathway to know it is wrong, and then we ask it to check its own work,
Aren't we just building a massive echo chamber?
yes, we're just asking it to aggressively rubber stamp its own bad code.
It is a profound blind spot. If you ask a model about a highly specific, obscure API endpoint and it hallucinates the parameters, asking it, "Are you sure?" doesn't magically inject the correct documentation into its neural network.
Right, it doesn't know what it doesn't know.
Exactly. It'll look at its own generated text, rely on the same faulty probabilistic pathways that generated the error in the first place, and just confirm its own hallucination.
Which is terrifying, honestly, because they always sound so absolutely certain.
They do.
I've had models explain a completely fictional Python library to me with the tone of a tenured computer science professor.
The sources emphasize this specific layer of the paradox, actually. LLMs are systematically overconfident, and this is largely a byproduct of their training, specifically reinforcement learning from human feedback, or RLHF.
Wait, I need to pause you there. I thought RLHF was supposed to make models safer and more accurate. How does human feedback accidentally train them to be confidently wrong smooth talkers?
Well, think about the human raters. During the RLHF phase, humans score the model's outputs. Humans naturally prefer answers that are coherent, well-structured, and authoritative.
We like people who sound like they know what they're talking about.
Right. We tend to penalize models that sound hesitant, repetitive, or unsure, even if that hesitation is factually appropriate for the prompt.
Oh, wow.
So the reward models learn to prioritize the tone of helpful authority. Statistically, the model will present highly uncertain information, where the actual underlying token probabilities are quite low using incredibly confident language, because that phrasing historically maximized its reward score.
It's like the ultimate smooth talker. It doesn't know what it's talking about, but it's going to make eye contact and sell you on the idea anyway, because that's what got it promoted in the past.
It lacks self-awareness of its own boundaries.
Yeah.
So when you rely on an unstructured evaluation, when you just feed the draft back to the model and ask, "Is anything wrong here?" the model defaults to its overconfident holistic state.
It's just scanning the vibe.
Exactly. It processes the text, sees that it is grammatically correct and sounds authoritative, and gives it a passing grade. An unstructured "looks good to me" from an LLM is just a rubber stamp.
So if unstructured self-evaluation is just a recipe for confidently deployed garbage, how do we fix the prompt? We have to make the evaluation phase of that loop actually function.
We have to move from unstructured evaluation to structured evaluation. You have to break the evaluation phase down into explicit granular constraints. Instead of asking, "Is this code correct?" you provide a highly specific rubric.
Right. This is the exact difference between casually asking a coworker at their desk, does my code look okay, versus giving them a mandatory 50-point code review checklist.
Perfect analogy.
If you ask if it looks okay, they glance at it and say sure. But if the checklist says, check for memory leaks, check for unhandled exceptions on database timeout, verify that all variables are strongly typed, you force a completely different level of cognitive engagement.
Yes. By forcing those specific checks, you push the model out of its holistic overconfidence trap and into an analytical mode.
Because it has to look for those specific things.
Right. When an LLM processes the instruction to scan text exclusively to identify unhandled exceptions, the attention heads in the transformer network allocate weight differently than when generating conversational text. You create a narrower, more objective lens.
It has to verify facts one by one rather than judging the overall tone.
Structured evaluation forces exactly that.
Okay, so structured checklists fix the theory. We're forcing specific attention allocation. But checklists are still subjective language processed by the exact same neural network. It still has the same training data cutoff. How do we introduce actual objectivity if we are trapped inside a single model's weights?
You have to break the silo.
Well,
Pure self-feedback is inherently limited. To defeat the self-verification paradox, you need external feedback. In the context of these frameworks, that means introducing ensemble approaches.
so bringing in a team.
You use multiple models or multiple generated samples from the same model to cross-check each other. Instead of generating one answer and evaluating it, you generate 5 different answers using a higher temperature setting.
Wait, you mentioned temperature. I thought temperature just made the model more creative or, like, random. How does injecting randomness help us verify hard facts or code?
Because temperature controls the variance in the model's token selection. A temperature 0 means it always picks the most probable next token. It is deterministic.
Right, it's very predictable.
But a higher temperature flattens the probability distribution, allowing it to pick slightly less probable tokens. By running 5 generations at a higher temperature, you are forcing the model to explore different pathways in its own latent space.
Okay, I think I see where you're going with this.
If Model A hallucinates a specific variable name because of some obscure quirk in its path, the variance ensures Model B or Model C likely won't take that exact same flawed path.
I see. We've moved from a solo developer checking their own work to sending the pull request to a completely different engineering team.
Exactly.
If the errors are random noise generated by high temperature, but the underlying factual truth is a strong signal, layering those multiple independent perspectives filters out the idiosyncratic noise.
You are bypassing the model's false confidence and relying strictly on the consensus of independent evaluations. The underlying factual truth tends to converge across multiple samples, while the hallucinations scatter.
Let's talk about the reality of building this, though. Running a 5-model ensemble, where each model is generating text, then running an evaluator model over all 5 outputs.
It sounds expensive.
I mean, isn't that going to absolutely torch my API budget? And what about latency? If I'm building a real-time application, the user can't wait 30 seconds for an ensemble consensus.
The token costs and latency trade-offs are significant, yes. Ensembles are expensive. You don't use a 5-shot ensemble for every minor chat interaction.
Okay, so when do we use it?
You reserve this architecture for high-stakes, complex reasoning tasks, things like generating database schemas, summarizing massive financial documents, or deploying infrastructure as code. You trade speed and compute cost for a massive reduction in hallucinated outputs.
That makes a ton of sense. It's a tool for the heavy lifting. But even with ensembles, we are still dealing with text evaluating text. Does any of this actually hold up when the model has to produce something strictly objective? Where is the proving ground for all of this theory?
The ultimate testing ground, and one of the most successful applications of LLM reasoning to date, is code generation.
Code generation is the ultimate test for self-reflection. I would have thought it would be something deeply analytical like legal analysis or mathematical proofs.
Well, think about it. Code generation acts as a natural laboratory because it provides the one thing that natural language usually lacks: clear, objective, undeniable feedback.
Because it either runs or it doesn't.
Exactly. If you ask a model to write a legal argument and then ask it to evaluate if the argument is persuasive, the evaluation is entirely subjective. It can argue with itself infinitely. Code either compiles and runs correctly, or it throws an error.
Wow, right. The model can use all the confident, authoritative language it wants in the code comments, but if it throws a syntax error or if it fails the unit test, it is objectively wrong. There is nowhere to hide.
Software engineering provides a binary feedback loop. The compiler doesn't care about the model's overconfidence.
No, it really doesn't.
If a Python script fails, that failure state, the specific traceback error, becomes a piece of hard external feedback. You feed that exact error traceback into the model as part of the next prompt. You say, you generated this code. It failed with this traceback error at line 42. Reflect on why it failed and generate a new version.
But hold on, compiler errors are famously cryptic. Sometimes a missing bracket on line 10 throws a cascading error that the compiler flags on line 50.
Right, which is a nightmare for humans.
Exactly. As humans, we have to hunt for the root cause. If the LLM is just guessing based on a confusing traceback, isn't it still trapped in its own flawed reasoning?
This is actually where the architecture of a large language model works to its advantage. An LLM parses the entire context window simultaneously using its attention mechanism.
Oh, it's not reading top to bottom like we do.
Exactly. While a human might scan sequentially from line 50 upwards, getting confused by the cascade, the LLM can instantly map the relationship between the structural tokens. It is highly adept at identifying structural mismatches, like a missing bracket or an unclosed string, across large blocks of text. The traceback just acts as a focal point for its attention mechanism.
So it takes the burden of error detection off the model's flawed internal reasoning and shifts it to an infallible external system. The model doesn't need to know its own blind spots because the compiler just handed it a map.
The model moves from being the generator and the flawed evaluator to being the generator and the corrector based on perfect external evaluation. It leverages the LLM strength, which is pattern matching and syntax correction, while completely bypassing its weakness, which is subjective self-evaluation.
So AI coding assistants aren't just getting better at writing code on the first try.
No. They are getting much better at using the compiler's feedback to run this reflection loop in the background before showing you the result.
It is iterating in the background. It writes the code, compiles it, sees the traceback, writes a reflection, fixes the code, compiles it again, gets a green light, and then presents it to the user.
It creates the illusion of one-shot brilliance.
That is wild.
For the builders tuning in, this is the blueprint. When designing an AI application, the core architectural question is, how can I create an objective feedback loop? How can I give my model the equivalent of a compiler error?
If I'm building an app that processes financial data, I shouldn't just ask the model if the math is right. I should have the model output a structured JSON and run that JSON through a standard hard-coded Python script to check the sums.
Yes.
If the script fails, feed the error back to the model. I use the deterministic code to check the probabilistic model.
That is the exact architectural mindset required. Let's look at the mechanics of parsing that JSON. You pass the initial generation to an evaluator prompt. That evaluator prompt is strictly constrained to output a JSON object with specific keys, perhaps a Boolean for error found and a string for error description.
Okay, keeping it very rigid.
Your application layer reads that JSON. If error found is true, your application automatically triggers the retry loop, passing the error description back to the generator model. You isolate the LLM to synthesize and parse unstructured data, and you rely on deterministic application logic to manage the evaluation flow.
We started tonight looking at the generative evaluate improve loop, which on the surface sounds so simple, but then we hit the brick wall of the self-verification paradox. We realized that a model checking its own work is inherently flawed because of shared knowledge gaps and the systematic overconfidence trained into it by human feedback.
The model basically operates as a smooth-talking echo chamber until we force it into rigorous constraints.
Right. We break the silo by replacing unstructured prompts with granular checklists. We introduce ensemble approaches, using multiple generations and higher temperature variants to filter out idiosyncratic hallucinations.
And we look to code generation as the ultimate proof of concept, where the unforgiving reality of a compiler provides the objective external feedback that makes true self-reflection possible.
So treating these models as static oracles is a dead end. We have to treat them as single components within a larger engineered system.
Exactly. And looking at the source material, there is a broader implication here that goes beyond software architecture.
Oh, where does this take us outside of the IDE?
We've established that code compilation provides the perfect feedback loop for an LLM to learn self-reflection because it is binary, objective, and external. But the vast majority of tasks we want AI to execute do not involve writing code.
That's true.
If objective feedback is the key to defeating the self-verification paradox, the question becomes, could we eventually design objective compilers for natural language and human logic?
Oh, wow.
Or will non-code reasoning tasks like strategic planning, legal analysis, or creative synthesis always remain too subjective for a model to truly self-verify without a human constantly in the loop to act as the compiler?
A compiler for logic. That is something to keep you awake tonight staring at the ceiling. The idea that we might one day have a deterministic system that can parse the validity of a philosophical argument or a business strategy the same way a Python interpreter checks syntax. Thank you all so much for joining us on this deep dive. To the software engineers out there, keep experimenting, keep building those loops, and whatever you do, do not let your models casually grade their own homework without a structured rubric. Have a great night, and we will catch you on the next one.